wind turbines have become part of America's landscape. From the green fields of Iowa and Kansas to the tornado valley of Texas and Oklahoma. From the shorelines of California to the barren lands of Nevada and New Mexico. These wind turbines generate much-needed electricity for millions of businesses and residents in the United States. Today, wind power is a major part of the renewable energy industry, which accounts for 20% of all electricity output in the United States. As the chart indicates, fossil fuels and nuclear energy still dominate the industry. But renewables, especially wind power, have been growing rapidly for the last few decades. Annual electricity output from wind power has risen from 6 billion kilowatt-hours to over 400 billion kilowatt-hours in the last 20 years. Currently, wind power accounts for 10.3% of total utility-scale electricity in the United States and 29% of all renewable sources used in power plants across the country. Globally, we have seen similar trends as the number of countries invested in wind power has increased from 16 to over 129, combining for a capacity increase from 3.6 billion kilowatt-hours to over 1 trillion kilowatt-hours of wind power in just 3 decades, accounting for 7.5% of global electricity output. So, what is wind power and how does it work? Wind power is the process of creating electricity using the energy of the wind. The process crosses 3 energy conversions. First, the kinetic energy of the wind spins the blades. Second, the blades spin the attached internal shaft, creating mechanical energy. Finally, the internal shaft spins an attached generator, which produces electrical energy or electricity. Electrical wires and cables then transport the electricity to the transformer and onto the grid for distribution. Previously, we have seen how electricity is generated using the concept of Michael Faraday's law of induction, which states that voltage or electricity is induced in a conductive material in the presence of a magnetic field. In power plants, the process involves large turbines and generators connected through a series of shafts. The rotating turbines create the needed magnetic field. Then electricity is generated in the generators, which host the conductive material, such as a copper coil. Previous generations of power plants used coal or natural gas fuel boilers to produce steam. Then, pressurized steam is used to spin the turbines. Today, many different sources of energy are used to spin turbines. Wind is one of those sources. By attaching blades to a turbine, the mechanical energy created by the rotating blades is used to spin the turbine. The turbine is attached to the electricity-producing generator through a series of low and high gear shafts. The role of the generator, or the way electricity is produced, has not changed. What has changed is the techniques used to spin the turbines. Before we get into the details of wind turbines, a bit of history on wind energy. Wind energy has been harnessed for thousands of years all over the world. Ancient Egyptians used wind power to sailboats along the Nile River as far back as 5000 BC. In addition, vertical windmills were used for grinding grain in Persia centuries ago. By the 9th century, windmills were common in Central Asia, China, and India before merchants brought the technology to Europe, where it was used to drain land for agriculture. Windmills were later introduced to the Western Hemisphere by European migrants. Ranchers and farmers, who settled the western United States, installed thousands of windmills for grinding grain and pumping water. The era of electrification in the 1930s led to the decline of windmills and the beginning of modern wind energy technology. Once used to do mechanical work, wind energy is now used to generate electricity. Wind energy boomed in the wake of geopolitical and climate change concerns in the 1970s. The oil embargo during the Arab-Israel War of the early 70s and the Iranian Revolution of 1979 led to an increased investment in alternative energy sources, including wind power, in the United States and other Western nations. By the early 1980s, thousands of wind turbines started to appear in the American landscape. Currently, there are over 70,000 wind turbines installed in the U.S., with 60% of them concentrated in 5 states. These top wind power producing states are Texas, Oklahoma, Iowa, Kansas, and California. In addition to increased capacity, the cost of electricity from wind power declined by nearly 70% from north of 30 cents per kilowatt to below 5 cents per kilowatt, making wind power the second cheapest source of electricity behind solar power. Globally, similar trends are observed. The process of converting wind to electricity requires numerous, expensive parts, such as a tower, blades, and a nacelle. The components are the biggest factors in determining the amount of electricity a wind turbine can generate. Bigger blades on a taller tower can capture more wind to run a bigger generator. The biggest wind turbines in operation today have an electricity generating capacity of up to 16 megawatts, supplying clean power for over 30,000 homes annually. The tower is the backbone of the wind turbine. It supports the blades, the hub, and the nacelle. The tower also houses ladders for crew members to climb up and down, as well as electrical cables to transport electricity from the generator to the transformer down below. Since airflows are faster, thus stronger at a higher elevation, taller wind turbines capture more wind, thus generating more electricity. In addition, since bigger blades and bigger generators lead to more electricity output, towers must be extremely strong to support the equipment. For example, some of the more commonly used 1.5 megawatts turbine models have nacelles that weigh more than 56 tons and a blade assembly that weigh more than 36 tons. For comparison, one of the biggest wind turbines, the GE Haliade X, has a nacelle that weighs 600 tons and a blade assembly weighing 225 tons. Wind turbine towers are made from steel or concrete. Steel towers are the most used type in the world. They are made in sections that are connected with wind tower flanges. All steel towers are in taper shape, meaning the diameter of each section decreases as the tower height increases. Because of their closed structure, the internal parts are well protected from the elements. Like the steel towers, the precast concrete towers are also manufactured in sections. All the sections are transported to the site and then assembled. These concrete structures have a large carrying capacity, allowing them to bear larger blades and nacelles. Finally, lattice towers are made from hundreds of steel materials, similar to traditional telecommunication towers. Since these towers are made in smaller steel sections, transportation is easier and cost is lower. Wind turbine blades resemble the wings of an airplane. Wind flows over the blades, creating a lift, similar to the effect on airplane wings, and causes the blades to turn. Aerodynamic properties are crucial in determining how efficiently the blades can extract wind energy. Blades start to spin when wind speed turns 6 to 9 miles per hour. This starting wind speed is known as the cut-in speed. As wind speeds increase, so does electricity production. Blades are usually fabricated from thin-walled fiber composite materials, with fiberglass reinforced polyester or epoxy. Carbon fiber or Kevlar is also used as reinforcement material. Carbon fiber has more tensile strength, higher stiffness, and lower density than glass fiber. It is also 20% to 30% lighter than glass fibers, leading to thinner, stiffer, and lighter blades. However, glass fiber is more commonly used due to its affordability. A nacelle is a cover housing that sits atop the tower and houses all the electricity generating components. The housing frame is made of front and rear frame parts. The front or main frame of the nacelle is generally made of cast steel and holds the yaw system, the gearbox, and the drive shaft that is connected to the blades via the hub. The rear frame is constructed of formed and welded steel and houses the generator, transformer, and electrical control cabinets. The nacelle is divided into three main systems: the yaw system, the mechanical drivetrain, and the electrical systems and cabinets. The yaw system is responsible for the orientation of the rotor toward the wind. It allows the rotor to head itself into the wind direction and keeps itself locked in that position when the wind direction is stable. The system is based on automatic signals from a wind direction sensor called an anemometer, which sits atop the nacelle. It measures the wind speed and direction and transmits the data to a controller. The controller, in addition to rotor orientation, is also responsible for starting the machine at a cut-in wind speed and shutting off the machine at dangerously high speeds to prevent turbine damage. The second component of the nacelle is the mechanical drivetrain, which is the powerhouse of a wind turbine. It contains the gearbox and the generator that is responsible for converting the rotation of the blades into electricity. The blades rotate at a low wind speed of 5 to 15 rotations per minute. At these low speeds, it is nearly impossible to generate electricity. The gearbox, which consists of several gears and shafts, speeds up the slow rotation of the blades by 100 times. The gearbox is one of the more costly and heavily weighted parts of the wind turbine. Thus, new kinds of generators, known as direct drive generators, have come to market recently. These generators are directly attached to the rotor and produce electricity at much lower speeds, eliminating the need for a gearbox. Lastly, the electrical systems and cabinets are made up of transformers and electrical wires. The electricity from the generators is carried down to a transmission substation via electrical wires. Turbines grouped over a large area are called wind farms. Wind farms provide power to the electricity grid of large-scale utility companies. They can either be on land, known as onshore, or on oceans and seas, known as offshore. Most projects today are onshore. Onshore wind farms require a turbine-to-turbine separation of 7 times the diameter of the rotor. Therefore, wind farms require a large acreage of land space. For example, the largest onshore wind farm in the United States, the Alta Wind Farm in California, has 600 turbines in an area of 3,200 acres or 5 square miles of land. Although most projects today are onshore, offshore wind farms are gaining acceptance rapidly. They are built on oceans and open seas to take advantage of the higher and consistent wind flow. On average, wind flows are 20% higher in the oceans compared to onshore. Thus, offshore wind farms generate more power at a more stable rate. Wind farms require greater financial investment, resources, and vast areas of open space. Therefore, they are only efficient and effective at the utility scale. For smaller clients, such as businesses, farms, and residential areas, small-scale wind turbines offer an opportunity to benefit from wind energy. Small-scale turbines are deployed in a wide range of locations at an elevation of between 30 feet to 140 feet. They can be installed on-grid, meaning tied to a central grid system, or off-grid for remote locations. However, because wind speed is slower and inconsistent at low elevations, small-scale turbines generate much lower power. In addition to cheaper source of clean power, wind energy is also creating new opportunities in factory towns across America. Over 530 factories across 43 states build wind energy-related parts. The wind energy sector generates the second most renewable energy jobs in the U.S.,